Welcome back to the LearnAPChem series here at LearnAP. In this video we're going to go over solids and their types. So we'll talk about what defines a solid, different types of solids, and then we'll also cover amorphous substances. As usual guys, if you've got a question on any of this, leave a comment, or you can also ask in the weekly live streams we do every Sunday from 5 to 6 p.m. Eastern for chemistry. Other than that, we'll get started. Alright, so let's start by talking about what defines a solid. Well, the first property is that solids retain their shape without a container. So think of like a block of wood. It's going to be shaped the same way whether or not it's in a container, and that's sort of the defining property of solids. Now this happens because of the strong attractive forces between molecules or atoms in a solid. So take for example table salt. I'm sorry, not LiCl, it should be NaCl. And we have basically a bunch of these with very strong attractive forces between them, which is sort of holding them together in the solid state. So that is why solids retain their shape without a container, is because of strong attractive forces between molecules or atoms inside that solid. Alright, so let's go over our types of solids, and there are sort of four main ones. And we'll start by talking about metallic crystals, and this is a crystal of metal nuclei and inner electrons. So basically every metal on the periodic table at room temperature is a metallic crystal with the exception of mercury. And so what this means is, let's say we have tin, Sn, is that a block of tin is just a large crystal of the nuclei of individual tin atoms and their inner electrons. Now this crystal can be thought of a sea of electrons because the valence or outer electrons of whatever metal you're dealing with, whether it's tin or iron, their valence electrons in a metallic crystal are thought to be sort of free. So if we have, say, a metallic crystal here, these individual atoms are retaining their inner electrons, but the valence electrons can sort of freely move through the crystal. And so you can think of it as a sea of electrons. And this explains metal's ability to conduct heat and electricity. Okay, so the second type of solid that you should know is ionic crystals. And this is a large crystal of ionically bonded compounds. So let's think about NaCl. What this really is that we have sort of the positive charge of the Na binding it to the negative charge of the Cl. Opposites attract. Well, in an ionic crystal, there's not just two, but there's a bunch of them. And so you form sort of this network, like so, where all of these are sort of attracted to each other, and it forms this this pattern. Note that this is the sort of strongest type of solid because these ionic bonds are so strong. One thing you should know is Coulomb's law, which is Q1, Q2 over R is the attraction. And this says that the strength of attractive forces in an ionic crystal depends on the charges, Q1 and Q2, and the distance from each other, R. So note that in an ionic bond, we often just say this, but in the real world, we actually just have a large network of multiple ionic bonds where the charges of these ions are sort of holding it together in this position. Alright, so our next type is molecular crystals. And this is a large crystal of covalently bonded molecules held together by IMFs. So if we think about our favorite polar molecule, H2O, we remember that the oxygen is negative, slightly negative, the hydrogens are slightly positive, and in this atom we have hydrogen bonds. Well, in a molecular crystal, these hydrogen bonds become strong enough that they're actually holding things together. So this is what would happen in ice. Note that a molecular crystal in general is not going to be as strong as an ionic, just because in these ionic bonds are very strong, but oftentimes in molecular, these IMFs can actually be sort of weak. So in water here, we have hydrogen bonds, but if I had something else that only had London dispersion, which is the weakest IMF, the bonds between, or not the bonds, but the attractive forces holding sort of this network together can be very weak. Okay, and the last one you should know about is network crystals or covalent crystals. And this is a large network of covalent bonded atoms. So think about graphite and diamonds is sort of all carbon, and this is an example of a network crystal, because what this really is it's just a giant chain of carbons all covalently bonded to each other, like this. Now this is contrasted with something like water, where in this network we have attractive forces that are sort of holding these together, but the attractive forces here between this positive dipole on hydrogen and the negative dipole on oxygen isn't actually a bond, but in a network crystal it is. So we have sort of a bunch of covalent bonds between these carbons, while here what's holding them together is IMFs. So that's the key difference between a molecular crystal and a network crystal. Alright, so finally let's talk about amorphous substances, and these can also be referred to as non-crystalline substances. Now these don't have a distinct melting point, but rather they gradually change phases over a large temperature range. So we all know water has a melting point of 0 degrees Celsius. So we'll say here we're at -1, and this is ice. But when we go from -1 to 1, this is just going to be regular old water. Now, an amorphous substance, we'll say here it's a solid, but as it goes to 1 degree, it's sort of gradually changing. So it might be a little bit solid, a little bit liquid, and it might just sort of stay that way rather than melt entirely or freeze entirely. Some examples of this is glass. Some people argue that glass is actually just a very slow moving supercool liquid, but probably the most accurate description is that it's an amorphous solid. And so the key here is that they don't have a distinct melting point, but they sort of gradually change phases over a large temperature range. So that's what distinguishes an amorphous solid or substance from just sort of a normal substance, like say water or pretty much anything else you can think of. Alright, so that brings me to today's challenge problem. What type of structure does LiNO3 form in the solid state? So the solution to this is on our website, as usual, learn-ap.com, and there will also be a direct link in the description that'll take you there. If you guys found this video helpful, please like and subscribe for future content. You can like us on Facebook and follow us on Twitter so that you never miss a live stream, which happen every Sunday from 5 to 6 p.m. Eastern, where we answer your questions about AP Chemistry. Links for that stuff will also be in the description. Leave a comment if you're still confused about anything, or also any other comments on the video in general. Other than that, I want to thank you guys for watching, and I will see you in the next video.